I'm not a scientist, but I've invited a couple friends who are to join us today. So would you please join us in welcoming them to stage? We have Victor Minces from UCSD's Listening to Waves program and Jackie Valentine from the Fleet Science Center.
Hello, Samir.
Hey, guys. Thanks so much for joining us. You know, I think we should start with the woodwinds. How do they work? How do they make sound?
Well, let's talk a little bit about what sound is. We're going to make a little experiment to see what sound is. I want everybody to grab your throat like this. I want to see everybody grab your throat, and go, ah. Can you feel the vibration in your hand? I bet you can, right? That is because you're creating a vibration, and that vibration is the sound generated with your vocal cords. Now, that vibration can travel through the air, and we will make another experiment to see how that vibration travels through the air, okay? Make your mouth like this, like if you were going to whistle, like this, and put your hand in front of your mouth, and let's see if you will be able to feel the vibration. Go, oh. Can you feel the vibration? Your hand is vibrating because you're transmitting the sound through the air to your hand. And your hand is vibrating in a very complex way, because when objects vibrate, they vibrate in complex ways. And in order to show that, we brought a demo here, which is called the Chladni plate.
All right, so this is the Chladni plate here. It's basically just a flat metal plate that is driven by a speaker, and that speaker is given sound from Victor's computer. As the plate vibrates at certain frequencies or notes, the plate will vibrate a lot at certain points and vibrate very little at others. The sand will kind of settle in the place where the plate is vibrating very little, giving us these great shapes. If we increase the note and make it higher, then those shapes will get more complex. Let's find another resonant frequency here. As you see, it will change. You can hear the note has also changed. If we go even higher, we'll get another more complex shape. Ta-da! Amazing!
Thank you. So I think I'm understanding the science of it. So for instance, a clarinetist would get sound created by causing the reed to vibrate, and the sound then would travel through the column that's in their instrument, and what comes out is sound.
Exactly.
Mm-hmm. So, you know, I think we should play a piece to put this science in perspective that features the woodwind family. So, we also have the brass family, and I'm curious how they make a sound, because I remember hearing something in The Thrill of the Orchestra about buzzing lips and all that tubing. How do brass players make a sound?
No, actually, brass players play the sound through their instrument similar to the woodwinds. They also use air for their instruments. But a major difference is that instead of having one set length of tubing, they actually choose different pathways for their air to move through, using valves like the trumpet or the French horn, or even stretching their instrument like the trombone might. For this demonstration, we're actually going to use these tubes here. We call these hoot tubes, and they're actually played using fire. I have a little torch down here that's heating up a bit of wire mesh in the bottom of this pipe here. And if we listen to the sound as that warm air moves through the tube, here we go. So you can hear that that specific frequency is tied to how long this tube is. We have a short tube and a long tube. The long tube being longer would play a lower note. This shorter tube plays a higher note, and you change different pathways for the trumpets and French horns and things like that.
But how do the brass players make their tubes resonate?
The way that they do it is actually they buzz their lips against a mouthpiece. They kind of make sort of a sound like that. And if we look at a video up here on the screen, we'll see in slow motion the mouth moving of a trumpet player. Very funny looking, you see that. And it moves so quickly. This is in slow motion. You see 175 kisses per second. That means that the mouth is open and closing over 100 times, or even in this case, over 200 times every second, getting that vibration started through that tubing.
So I think I'm understanding this. The brass players create a sound by buzzing their lips into their mouthpiece, and that causes the vibration of the sound waves. But because the tubes are so long, they create lower pitches, and also by the time we hear the sound, it's that big, beautiful, brassy, glorious sound that we love.
Absolutely.
Exactly.
I think we should play a piece for the brass instruments, don't you think? You know, the string family is the largest family of the orchestra. But when I look at their instruments, I don't see mouthpieces, I don't see reeds, I don't see any of this. How do they make a sound?
You're actually very, very right. Now, with the string instruments, they aren't using their breath or air really to get their vibrations moving. They're using friction. And if we look at the next video on our screen, you'll see a close-up of the bow that they're using actually playing on their string. You see it pulls on the string very, very slightly, and then it kind of lets it go, which creates several vibrations every second. To kind of help us understand that, we're going to use a similar kind of demonstration. On their bows, they have this sticky stuff called rosin, and in their case, they use it in the form of a block. I'm going to use it in the form of powder here. And this is what I'm going to use as a string. We call it a singing rod. It's going to work the same way. I have this rosin which makes my fingers sticky, and as I rub my fingers on this rod, I can get all those tiny little vibrations to happen. I just move my fingers and they'll kind of stick and slip and stick and slip hundreds of times every second, getting the rod to vibrate at its own resonant frequency. Similar to the hoot tubes and how it's going to have its own single note for how long it is, but the violin players and the cellos, they can change their pitches by pinching their string at different points.
So in other words, Jackie, when a cellist or a violinist, they make a sound, in other words, by they use an object to rub against the string, right? But a string is very similar to this metal rod. So they use their bow to make a sound, I guess. But what about, in the thrill of the orchestra, we heard about this word pizzicato, or plucked strings. Maybe you remember that. Now, how does that scientific principle apply to making a sound?
So you can think of pizzicato as being one very large impact at once rather than hundreds of tiny little ones. So they're about equal, except for that the one large pluck is much louder at once rather than a bunch of tiny little ones.
So I think we should play a piece for the string family, don't you think? But this time, let's have it be entirely pizzicato. So we have one more family of the orchestra left, and they're a very important family, the percussion family. They provide the rhythm and the heartbeat for all of us here on stage. But Jackie and Victor, I know that there must be more to it than just taking a stick and hitting a drum, right? What's the science behind percussion instruments?
Yes, so percussion instruments are those that you can hit. And percussion instruments come in two flavors. Some of them have a pitch, and you can make melodies, you can make songs with, and some of them don't have a pitch, and they are really good for making rhythms. In order to understand the difference of pitch versus non-pitch, we'll use a scientific tool that we, the scientists of music, use all the time, and it's called a spectrogram. And as you can see, or you can guess, the spectrogram is responding to sound. Now, if you make a really, really loud sound, you can make it turn yellow and green and red. So let's try to make a really loud sound and try to make it turn red, okay? So when I count to 3, we will all clap and yell. 1, 2, 3. Ah! Okay, I was turning red. So you can see that the spectrogram is responding to sound, right? Now, it doesn't just tell you how loud the sounds are. It can also tell you what pitch there is in a sound. And in order to show that, I brought this musical instrument. It's a pitch percussion musical instrument that I made at home. And I will play one note. Now, that line over there tells us the pitch of that note. Now I will make a musical scale with the pitch going up. And I want you to follow the lines and see that they also go up, okay? 1, 2, 3.
Bravo!
Okay, so as I said, not all the instruments have a pitch, and some of them not. And some of them those instruments that don't have a pitch look very different in the spectrogram. And maybe Samir, can you play the sandpaper for us to show us how a non-pitch instrument looks in the spectrogram? Thank you very much. So you see that it doesn't have any of those horizontal lines. That is because it's not making a pitch, and it's really hard to make melodies with it. Samir, do you think you could play a musical scale with the sandpaper? Thank you. So it's really hard to play musical scales with a sandpaper with a non-pitch musical instrument, but it's really good for making rhythms so you can dance.
I think I understand what you're saying, Victor. So percussion instruments come in pitched instruments, like a xylophone, or unpitched instruments, like a drum. And, you know, percussion instruments really are all around us. They're anything you can shake or strike or scrape. And I'm really intrigued by these two sandpaper blocks, and I think that perhaps we should invite our percussion family out to join us by playing a piece that uses sandpaper blocks. Would you guys like to see that? This is called the Sandpaper Ballet by Leroy Anderson, featuring our percussion family.